Okay, so good morning, everybody. Last week we finished Unit 1. Now, Unit 1, um, called the Introduction to Environmental Chemistry, very short, very small unit, not really much in that unit to, um, I guess, no. I mean, a lot of it was high school kind of chemistry definitions, what is chemistry, what is environmental chemistry. And then we did learn about what some of the things that they do, like doing the cleanup and regulation and monitoring. So those are some things you guys might want to know for an upcoming quiz on D2L. Remember, guys, these quizzes are online and you can have the day to do them, or more than a day even, and that means you can use your notes. So just keep your notes handy. If you don't have a printer, just keep them open on D2L or on your phone or tablet or laptop, whatever you have. So today I'm going to start Unit 2, and this kind of brings me to the topic of labs. So guys, I mentioned to you last week we had no labs, and on Sunday we had no lab. And when you look at your schedules, you'll see 2 lab sections a week. And because of the corona, staying from home, because of even Ramadan as well, we will be looking at around 1 of those labs a week. So the other lab section, the Sunday morning one, that's just free time for you guys. You can ask me questions if you want. We can have a Zoom chat, up to you. But every Wednesday for the next few weeks, so tomorrow, late in the afternoon around your lab time, I am going to upload a video and give you a lab activity, and you can take the week to do that. So tomorrow, late afternoon, your lab tomorrow is around 2:00 p.m. and I'm going to videotape this myself and upload it around 2. You don't have to come to Zoom. You don't have to be anywhere. But around tomorrow afternoon, I'm going to upload a video kind of showing you the lab equipment. And all of these labs will be based on water chemistry. So they will be based on Unit 2. And then you can watch the video, and there will be a D2L assignment that I will post, and that will be due next week. So again, when you see the lab on your schedule, you don't have to be anywhere at that time. It's just at that time. I'm available for questions, and I will upload a short video, a demo, like a demonstration, and then you guys will have a D2L quiz about that. The video will be on YouTube. You can watch it whenever you want. You can watch it at midnight. You can watch it at 7 in the morning, and the quiz will be open for a week. So every Wednesday, I will upload a new video, and you guys will have a new lab activity. And this will make a little bit more sense tomorrow. When you see the video and you see the D2L quiz, you'll kind of get an idea for it. And again, if you guys have any questions, I'm available. You can send me an email. We can set up a Zoom meeting. So I just wanted to get that out of the way. Tomorrow afternoon, there will be a video and a small quiz, a lab activity going on D2L, and you'll have a week to do that. So that won't be due until next Wednesday. And then next Wednesday, we'll have another lab, and we'll do at least 5 labs. Anyways, let's get back to the notes here. This is a really cool unit. This unit is 100 and something slides, 180-ish, I think. This will take us most of May, most of the course. And as you can see, guys, it's about water chemistry. So we will, start with chemistry, stuff you guys would have learned in Chemistry 1200. So I'll go a little quick through this. This is stuff like polarity and density, things you've already learned about, again, in 1200. I don't know who you had, maybe Miss Michelle or Miss Gabby or Mr. John, if you were here years ago, but we'll start with water basics. So we're going to look at the makeup of water, polarity, pH. My favorite part around the bottom the boiling point, melting point, density. This is actually really important down here for a future question I might ask you guys. Uh, the chemical and physical properties of water are amazing. Like, I don't know if you've ever sat and thought about water, and I know it's kind of weird, but uh, just the reason for, I guess, it's hard to explain. There's so much we could talk about water, like the way fish can survive in the winter, and the way that ice freezes, and it's just super cool. So we'll kind of talk about that towards the end of maybe today, maybe on Thursday's class. Okay, so slide number 1. This is something you are expected to know, not these numbers perfectly, but this kind of idea here. Water is the most abundant compound on Earth's surface. Now, notice I said compound. I didn't say element. Okay, so I'm not talking about elements. I'm not talking about metals in the earth crust or things in the air like nitrogen would be the most abundant element in the atmosphere. I'm talking about compound. And if you can't remember from Chemistry 1200, a compound is when 2 or more elements get together and form, a compound, a substance. So H2O is our most abundant compound, covering about 70% of the Earth. Now, this is what's really interesting. 98, I'll round up, about 97.5% of all that water on Earth is not drinkable. It's salt water. Now, I know here in Qatar, we desalinate the ocean. We remove the salt from the ocean water, and that becomes drinkable water. But without desalination or any type of purification process, this water is not drinkable. It's in the ocean mostly, and it's salt water. So 97.5% of all the water on Earth is salted. 2.5% of the water on the Earth is fresh water, readily available, readily drinkable. And I know where I come from in Canada, we have, I think, one of the world's largest supplies of fresh water because, again, the country's so big. There's a lot of freshwater lakes and rivers in that country, in my country. And then you can see about 1.7% of that water is held in polar ice caps and glaciers, so it's frozen. And of that 2.5% fresh water, the 1.7 that's frozen, only 0.77, so less than 1%, is readily accessible for us humans. So when you hear about or think about water on the earth, less than 1% of that water is available in lakes and rivers and ponds for us to drink. Pretty crazy. So you guys don't need to memorize these numbers. You'll have your notes with you when you do a quiz or something, or even in a month or two, the final exam. But just know that most of the water is salt, only 2.5% is fresh, and less than 1% is available for us. Now, another really cool property of water is that it exists in nature as solid liquid gas. One of the few compounds or even elements on Earth that you can find in all 3 phases in one place. Remember what we call these states of matter or chemical phases. So, maybe not in Qatar, but I know where I'm from right now in Canada, there's still snow. So you could go outside right now and look, and you would see snow on the ground. So that would be solid water. Snow is just ice. You could look and see, in the roads or across, again, where I live, you can look across from my house and see a lake or a bay. That's liquid water. And then you could look up into the sky and see clouds, and that would be gaseous water. There's gaseous or gas phase water all around us all the time. When you guys hear the word humidity, that's water in the air. So all around us at all times, water can be liquid like we know it, just running water, solid like ice and snow, and then a gas like in the air or clouds in the sky. Okay, pretty easy. I mean, this is pretty common sense stuff. Now, this is maybe not common sense. Oh, I should ask, by the way, I didn't ask this. You guys can see my slides, right? You can see PowerPoint. You want to let me know in the chat? Can you see my slides? Okay, thanks. Thanks, guys. I should have asked earlier. You know, I never trust Zoom. Sometimes it doesn't show the right thing. Anyways, this is not maybe a property of water that somebody, you know, very young will, but you guys would know this from Chemistry 1200. One of the properties of water is that the three-dimensional shape, I say we used to, but in Chemistry 1200, oops, you call this valence shell electron pair repulsion, the VSEPR shape. You probably use model kits, or I mean, at least you knew the shape. It would be a bent molecule. The idea is it has two lone pairs up here. These are unbonded electrons. And then here we have bonding pairs bonded to the hydrogens. So this, guys, is the molecule of water. I mean, you guys know that, but the fact that it's bent is really, really important. Because it's bent, it means it's polar. Here's my molecule here, guys. I'm sorry. And the picture I took didn't have lone pairs on it. So let's put those lone pairs up here. Whoops. Okay, so there you go. Now, this is from Chemistry 1200. You don't need to memorize or know much about the shape. I mean, we're not going to, in this course, talk about lone pairs and bond angles. We're not even really going to talk about VSEPR, valence shell electron pair repulsion. I don't know if you guys remember that, but you had shapes like tetrahedral and trigonal pyramidal and trigonal planar. We don't need to worry about that. But what we do need to know is that water is bent, which means, and this is, I guess, one of our first really important things today, water is polar. A very important feature. One of the most important properties of water is that it is polar. Now, when I say polar, you did this in Chemistry 1200. Just think of like a magnet. A magnet has like a positive end and a negative end, you know, north and south pole. Think of a polar molecule very similar. In the polar molecule of water, you have a negative end, and again, a slightly negative end. Slightly because this delta sign here means it's slightly negative. It's not ionic. These are covalent bonds, meaning the electrons are shared. The only thing is most of the electrons are shared nearer to the oxygen. It has a higher electronegativity. Again, guys, I'm throwing all these things at you that you learned in 1200. If you can't remember what electronegativity is, it's an element's attraction to an electron. So oxygen wants electrons a little more. It pulls the electrons a little bit more towards itself, and this creates a positive and negative region. So for water, the positives are here, the hydrogens are slightly positive. Oops, I don't know how to fix that pen jumping around, but anyways, the hydrogens are slightly positive, the oxygen's slightly negative. So this creates, again, you can think of like a magnet or a you know, Earth, the north and south pole. We have a negative and positive pole. Again, I'm going a little quicker than I normally would because you did this in 1200. But this is, I always make the joke, but this is really important. Water is polar, so it has, in terms of intermolecular forces, if you remember those, the forces between molecules, it has London dispersion, everything does, and it has dipole-dipole, or polarity, right? It's a polar attraction to each other. The positive and negative ends are slightly attracted. But this also leads to one of the other intermolecular forces, Again, I don't know if you guys remember those intermolecular forces, but the other one is hydrogen bonding. So water has all three. Let me just do something for you guys. IMFs, if you can't remember. Now, you don't need to remember this for this course. You should know that water has all three. So just a little review in Chemistry 1200, you learned about London dispersion. Basically, all molecules have this. It's a very weak intermolecular force. This is where water gets different. Water also has dipole. Okay, this is because it's polar. And water also has hydrogen bonding. Hydrogen bonding happens when a hydrogen is bonded to an F, an O, or an N, a nitrogen, and sometimes Cl, but we won't get into that in this course. So water has all three. Because water has all three, that's one of the reasons why it has such a high boiling point. A lot of molecules, guys, don't have high boiling points. Think of carbon dioxide. It's boiling right now in your lungs. And I know, when you think of boiling, you think of, burning and hurting you, but boiling is just liquid to gas. So oxygen, carbon dioxide, carbon monoxide, nitrogen, all of these chemicals are boiling in the air around you right now. Water does not boil at, what is it now, 30, 35 degrees? Maybe in your, where you live, it's probably 20, 22. They're all boiling. Water boils at 100, excuse me. And that's because it has all of these forces. Okay, so if I go back to the last slide here, hydrogen bonding is the strongest intermolecular force. And hydrogen bonding explains many of the properties of water. Some of the most interesting properties of water are explained by hydrogen bonding. And I always tell my students, and again, it's a little different because we're online right now, but if you guys are writing an exam or a test and there was no notes, couldn't use your phones, you were in the classroom, and you wanted, if I asked you, why does water do this? Why does water do that? 99% of the time, the answer is hydrogen bonding. So I always tell my students, if you're not sure why water has a certain property, it's probably because of the hydrogen bonding. All right, so that's a good kind of help for you guys, because I will ask you about some of these properties of water, and I will ask you, why does it happen? And the answer is 99% of the time, hydrogen bonding. Hydrogen bonding, by the way, is basically like dipole-dipole forces, but very strong because of the differences of electronegativity. So there's not a huge chemical difference between dipole-dipole and hydrogen bonding. It's just that the differences in electronegativities between hydrogen and chemicals like oxygen, fluorine, and nitrogen are so big that the attractions are even stronger. So, I mean, that's it. That's chapter one, or sorry, section one. You guys will definitely see some questions on this. Before this week is over, I'll probably have a little quiz for you guys. I mean, I know you have a lab to do, but I will also have a short quiz about chapter one and a little bit of chapter two. We're looking at, maybe 4 quizzes or so, maybe 5 quizzes throughout this semester, a couple of labs, and then your final. So, nothing too crazy. I won't keep you too busy for intersession, I promise. All right, cool. So, oh, that's not, sorry, I thought the chapter was over. I put the slide in there. These guys, if you've never heard of these guys, I say these guys, I think their last name is Green. There's John Green and another guy. I can't remember their last names. One of them wrote the book, Fault in Our Stars, if you've ever read that book. But these guys have a really, really good science channel on YouTube called Crash Course. And Crash Course is very, very old. Now, later in this course, guys, I might get you to watch a video in class or something. I won't bother getting you to watch this video. Or sorry, I won't show this video right now, I mean, because there's nothing in it that I kind of haven't explained or will explain. But if you're confused or you don't like how I explain something or you want to learn a bit more, you can watch these guys, these links here. These links, if you're using your PDF, you might not be able to click the link, but all you have to do is go on YouTube and type in Crash Course, and you could type in Biology 2 or Crash Course Water, Liquid, Awesome, whatever you want, and this will come up. And these guys are really fun, really good, lots of animations. I highly recommend checking these guys out. All right, so it's 11:10. I'd like to do a bit more of the properties of water. I'd like to maybe get to density, and then we'll check the time, and we'll see how we're doing for time after I get to density. These are 2-hour classes, but just the way that this course is, I won't go 2 hours, and there's not a lot of room in these courses for practice or like me to give you questions to do and I can kind of walk away. It's going to be a lot of me talking. I really apologize for that. So I won't go too much longer. I'll do just 3 more properties very quickly, and that'll be it for today. All right, so properties of water, pH. So I don't know if you got, I should know because I've taught all these courses. I guess if you guys did 1201 or 1210, you would have learned about pH. If you haven't learned about pH at the college, you probably learned about pH just in school, I would imagine. pH, and I should have an explanation of what pH is here, but I don't. I kind of assume you guys know. pH is the measure of the acidity of a chemical. More specifically, pH is a measure of the hydronium ion concentration, or if you really want to think about it quite simply, H+. Now, this is a different definition of acid. Man, this pen. I'm not going with the most technical definition of acid, but it typically measures, or well, pH does measure the amount of hydronium ion, and this is the compound formed when you mix H+ with water. So don't worry, we're not getting into chemical reactions. You don't have to balance anything, but you should know that pH measures the strength of an acid. The pH scale, by the way, if you can't remember, goes from 0 to 14. Base is over here, acid is over here, and then at 7, you have water, or well, sorry, I shouldn't say water. At 7, you have neutral. Okay, so anything less than 7 is acidic, anything bigger than 7 is basic. One of the labs that we'll be doing towards the end of the semester, where we will look at the pH of water. Okay, so water. Technically, I say this very loosely, but in theory, water should be 7. In real life, water is not 7. The reason water is not neutral in real life is because of things dissolved in that water. So let's take carbonated water, like fizzy water, one of my favorite drinks. I guess it's called club soda or just sparkling water, whatever you guys call it. That has carbon dioxide dissolved in it. That's why it's fizzy. The carbon dioxide are the bubbles. And carbon dioxide is acidic. It forms carbonic acid in water. So soda water, things like Pepsi, Coke, 7-Up, just plain soda water, they are acidic. because of the CO2. And that's, I think, why they, your dentist might say it's bad for your teeth. Besides all the sugar, they're acidic. Bottled water, and especially guys, if you buy named brand bottled water, you might see things like alkaline water or, there's so many brands out there. Bottled water is typically slightly basic. And again, it's because it has different element or different chemicals dissolved in it. I know bottled water has a lot of I think maybe magnesium or calcium. You can look at the side of a bottle of water and it tells you exactly what's in it in terms of ions. So some of these ions would make it basic. Pure water, however, would be 7. Now, is this up top? You might have done this in 1201 or 1210, whatever you did. All you need to know from this slide is the bottom. Technically, the pH of pure water is completely neutral. The amount of acid equals the amount of base. Acid, base, neutral. The 7 comes from that number. Again, we're not going to get into that in this course, but you should know the pH of pure water is 7. In natural waters, so again, I'm not talking about sparkling water. I'm not talking about bottled water. I mean naturally. So a lake, a river, a pond, a stream, the pH is controlled. Governed just means controlled, by a lot of factors. Big factor is carbon dioxide in the atmosphere. So I mentioned this last class. One of the big issues that I shouldn't say I see, but one of the big issues I think about when I hear or read about global warming is the amount of carbon dioxide that we put into the atmosphere. So you guys hear about global warming or climate change, I should say, and you hear about the earth getting warmer, the ice caps melting. But one of the big issues, and Australia, and I mentioned this last class, Australia sees this now, the amount of carbon dioxide dissolves in the oceans. Okay, when you put carbon dioxide into the atmosphere, well, the ocean is just like a big, solvent, right, waiting to dissolve things from the atmosphere. And one of those is CO2. So as CO2 gets more and more dissolved more and more, the pH gets lower and lower. It becomes more acidic. And we noticed the acidification of the oceans, especially like shallow waters around the Great Barrier Reef in Australia. The acidification of these waters is really harming the ecosystem. It's killing, or what they call it, bleaching the reefs. You'll see later in the unit that, or in this course, that certain fish or sea life can only live in a certain pH range. So as we make the oceans more acidic, we're really affecting things like the reefs, the fish, the plants and animals in the ocean. Water left exposed to the air will dissolve carbon dioxide, and it will form carbonic acid. So carbonic acid is H2CO3. Again, that's when you put together water and CO2, right? You can see very simple chemical reaction. 2 hydrogens, 3 oxygens, 1 carbon, right? Very simple reaction. This can turn the pH from 7 down to about 5.7. The limiting pH, meaning about as low as the carbon dioxide will make it, will be 5.7. Now, it doesn't need to be acidic. It doesn't need to be neutral at 7. It can also be slightly basic because of different things dissolved in the water, like alkali metals. So this is good to know. All over the world, wherever you take the sample of water, we're going to look at water sampling tomorrow. Wherever you sample the water, natural fresh waters can range from 6 to 9. Okay, ideally or normally they're closer to 7, but they can be acidic or basic from 6 to 9. All right, so I put a star there. You might see that question come up on a quiz. I might say, The pH of natural fresh waters is usually blank, and you would fill it in 6 to 9, or it would be multiple choice, something like that. But you should know that natural fresh water all over the world, the range can be a slightly acidic or slightly basic. Okay, I'm going to do heat capacity and density, and then I'm done. You don't have to listen to me talk anymore. Oh, heat capacity. Now, this is a term. I don't know if you guys did this. I know my engineering students do this in a course called 1121. They do a whole chapter on thermochemistry. I don't know how much you guys have done. Again, I've taught all these courses, but I can't really remember every outcome. But it's a pretty simple concept, and it is related. If any of you guys like to cook, you know, especially now with the lockdown, I don't know if you guys are baking more bread or cooking more. I know I certainly am, just to keep myself from not going crazy. I've been baking or cooking, and heat capacity is directly related to cooking. And I'll explain in a minute, but let me first tell you what heat capacity is. Heat capacity, they do this in physics, we do this in chemistry. It's a physical quantity of a chemical, and it's equal to the amount of heat added to a chemical or substance and its temperature change. So different chemicals have different heat capacities. And again, what that means is the amount of energy required to heat that chemical up. The actual definition is here on the bottom. I will read this definition word for word, but then I'll explain it. So specific heat is the amount of heat. Now remember, heat, it's just energy. We measure it in, joules. So heat is just energy. So specific heat is the amount of heat needed to raise the temperature of a certain mass by 1 degree Celsius. And I'll talk about what that number is for water in 1 second. But specific heat, every chemical has a different specific heat. It's the amount of energy it takes to heat it up. So I just want you to think about something. You're in your kitchen, okay? And I want you to pretend you're at your stove. You're at your oven and stove. And on the top of the stove, you have boiling water, okay? So, I mean, let me just kind of make a little picture for you. So, you know, you got your stove here. I'm not an artist. There's your stove. And on top, you have your burners. And on that burner, you have boiling water. Okay, 100 degrees Celsius. Now, in your oven, you've turned your oven on, and say you're cooking something, I don't know what it is, but you've turned your oven on. And I mean, we can even go crazy. Like, again, I don't know if you guys cook, but you know, if you wanted to make potato, like French fries, or you wanted to cook fish or a chicken breast in the oven, you would probably heat your oven up to almost 200 degrees Celsius. Okay, almost, you know, depending on what you're cooking. So think about this. You're facing your stove, you got boiling water on top that's at 100, and then you have air in the oven at 200. Just imagine now taking your hand and sticking it into the boiling water, okay? You would burn yourself. You'd be at a Hamad hospital within the hour, right? If you put your hand into the 100 degrees Celsius boiling water, you would burn your skin very, very badly. Now, think about reaching into an oven that's 200 degrees Celsius, obviously not touching the pan or not touching any metal, but just putting your hand into that oven. No problem. I've done it. I do it every day, right? When I cook, I'll put my hand in the oven. I might have like a tea towel or a towel to grab the pan, but in the air in the oven, as long as I'm not touching any metal, my hand is fine. So how come I cannot put my hand in 100 degrees Celsius water, but I can put my hand in a 200 degrees Celsius oven? Again, guys, not touching the metal. Do not touch the metal. And the answer to this is the heat capacity. The amount of energy stored in the water versus the amount of energy stored in the air is completely different. Water has a very high heat capacity. So it takes a lot of energy to heat water to 100 degrees Celsius. So when you put your hand in that water, all of that stored energy, all of that heat energy is transferred to your hand. You burn your skin. In the oven, air, and air being a mixture of gases, has a very low heat capacity. And because the heat or the energy that it takes to heat air up to 200 degrees Celsius is so low, it doesn't take a lot of energy to heat air. You can put your hand in and energy is transferred. Your hand will feel warm. I mean, you wouldn't be able to put your hand in there for too long, but it wouldn't hurt you, not for at least 10 seconds. So I don't recommend trying this entire experiment from home. But next time you guys are baking or cooking, just think about it. When you put your hand in the oven, how come 200 degrees Celsius doesn't hurt? It's about heat capacity. So water has a very high heat capacity. Excuse me. Now, guys, the answer's on this slide, but I want to see who's awake here, who's still listening. If I asked you, what chemical property results in water having a high heat capacity, what's the one chemical property I told you which gives water all of its cool properties? So remember, we had London dispersion, dipole, hydrogen bonding. You know, why does water have a high heat capacity? And then Nora and Sophia, thank you for the answers. Hydrogen bonding. I'm kind of laughing here because you're going to see this with density. You're going to see this with viscosity. Every property or interesting property about water is basically because of its hydrogen bonding. Hydrogen bonding is a strong intermolecular force. It's holding the water molecules. I shouldn't say holding, but it's creating a very high attraction to these water molecules. So to boil them, to heat them up, to turn them into a gas, to break these intermolecular forces, it takes a lot of energy. So water has a very, very, very high heat capacity. And guys, it's 11:30. I'm going to do 2 more slides and I think I'm done, because the density topic that I want to teach you, that takes a little bit of time. So 2 more slides and we'll finish. Well, I mean, this slide and 1 more we'll finish. But this is really important. I wish I could put like an emoji on my, oh, that's a horrible wink face. There's my wink face on the bottom, winking. This is good to know. Because water has a high heat capacity, because of its hydrogen bonding, water is one of the chemicals that can moderate Earth's climate. Now, I don't even mean, I'm not even talking about climate change in general. I mean, literally, the reason Earth isn't a big ball of hot rock floating around the sun or orbiting around the sun, one of these reasons, our atmosphere, but the other reason is the amount of water we have. It's a giant heat sink. And I don't know if you know what that term is, or if any of you are into computers or building computers. A lot of computers get very hot. And sometimes in most computers, there's a heat sink. There's a part of the computer that would absorb a lot of heat. It's usually near the fan, and the fan will blow the hot air away from the heat sink. A heat sink is something used to control temperature by absorbing heat. And water on the Earth's surface is a heat sink. All of the warmth from the sun, I shouldn't say all of it, but much of the warmth from the sun is absorbed by the water, like a big sponge. And because water has such a heat capacity, such high heat capacity, it can absorb a lot of the energy from the sun. And without the water absorbing that energy, the climate of Earth would be very, very, very hot, much warmer than it is. And again, this is a twofold process. It has to do with the atmosphere, but a big thing is the water on the Earth's surface is absorbing much of the heat from the sun, and it buffers, which means protects us from fluctuations or changes in the temperature. So the reason the temperature of the Earth kind of stays within a certain range, a lot of that, yes, the atmosphere, and the other reason, the heat capacity of water. So guys, the last slide I'm going to do today is, again, I know I technically have another 30 minutes or so, maybe more, but there's only so much I think we can do in one day. And this density topic is super interesting. And I'll save it for tomorrow or Thursday. Anyways, last slide. According to, I don't know who this guy is, excuse me, Josh Willis, whoever he is. But I found this on NASA. The oceans absorb 1,000 times more heat than the atmosphere. Okay, so the the waters are holding 80 to 90% of the heat of global warming. So, like again, when we hear about climate change, one of the first things you hear about is sea level rise, and it's because all of the extra heat trapped in the atmosphere. So again, the temperature of the Earth might only go up 1 degree Celsius, but the oceans have absorbed a lot of that energy, which is again subsequently hurting the plants and animals and melting the ice. So because of the heat capacity of air compared to the heat capacity of water, I want you to think about my oven example. Think about the pot of boiling water on top and the oven in the bottom. The oceans are the pot of boiling water, and the oven is the atmosphere. And it takes a lot more energy to heat up that water. So the oceans are absorbing much, much more energy. Okay, sorry guys, I know this is maybe some of you, this might not be the most fun stuff. I personally find this very interesting, but I'm a weirdo and I love science, I love chemistry, I love water. It's such a cool chemical. So Thursday's class, we will talk about density and viscosity, all right? And then, oh, maybe not the most fun thing, there's some legal stuff at the end of this chapter or section. So that's it for me today. Don't forget about your class on Thursday. It's 1:20 p.m. with the Ramadan timing. So I'll see you guys on Thursday at 1:20. The other thing is tomorrow afternoon, I will have a small video uploaded and a small activity on D2L. And this will be your first lab. You do not have to be here tomorrow, okay? You can watch this and do the activity whenever you want. You can do it Friday, Saturday, Sunday. You can do it Wednesday night. I don't care. But you don't have to show up to Zoom. You don't have to do anything like that. It's this is a lab that you guys kind of do on your own time. And I will put that up tomorrow afternoon around 2 o'clock. Okay, and the labs, you guys, you will have a week to do them. So every lab will be on Wednesday and then do the next Wednesday. So Wednesday to Wednesday. Okay, guys, tomorrow you'll see my face. I was joking with my friend. I haven't shown you even what I look like yet. I never turned my camera on last semester because all the students knew what I look like. And I apologize, and I would have shown you my face today, but my hair is crazy. I need a haircut so bad. So anyways, tomorrow there'll be a video of me doing the lab, and you'll see what I look like. All right, so cool. Have a great day. I'm going to hit stop recording, and I'll see you guys on Thursday. Bye. If you got any questions, let me know in the chat.